Hello everyone. This lecture is exclusively recorded for first year BSc student of BK Birla College Kalyan. This is Calculus paper Mathematics 1. In this lecture, we will prove the density theorem of rational number and irrational number. So let us write down the statement and we will also prove the theorem along with the application of theorem. So, density theorem of rational number. So the statement is as follows. If x comma y are any two real number such that x less than y, then there exists a rational number say R1 such that x less than R1 less than y. Very simple statement. It says that if you have any two real number, then it is always possible to find out a rational number between these two real numbers. To prove in this proof, we will be using an Archimedean property to prove this result. So let's prove this. So there are some assumptions which I'll assume to prove this. So I'll assume that x is strictly greater than 0. Since it is given that x is greater than less than y, so this would imply y minus x is greater than 0. If y minus x is greater than 0, this would imply 1 upon y minus x is still greater than 0, and this 1 upon y minus x will belongs to real number. So we will apply an Archimedean property on 1 upon y minus x. So by Archimedean property, there exists a natural number say n such that 1 upon y minus x is strictly less than n. This would imply 1 upon n is less than y minus x. This would imply since n is a positive, if I divide n by n, then I will get 1 less than ny minus nx. What does this mean? This means if I draw this on a real line, so my nx lies between here, ny lies between here. So it says that the distance between ny and nx is bigger than 1. When I say ny minus nx, it means that the distance between ny and nx is greater than 1. If the distance between ny and nx is greater than 1, this distance is greater than 1, that means definitely there will be an integer between nx and ny. So from geometrically you can easily see this would imply there exists an integer say m such that m lies between nx and ny. Since n is non-negative, it is strictly greater than 0, you divide it by n. So I will have x less than m by n, which is less than y. Since m is an integer, n is a natural number, so m by n will be a integer upon integer, you can say, because every natural number is an integer. So it's a ratio of two integers where n is not equal to 0. That means it is going to be a real rational number. So this is basically a rational number. So let's call so what I will do, I will call, so this would imply x is less than r less than y, where r is equal to m upon n, which belongs to rational number. So I have proved that between two real number x and y, there exists a rational number r such that that rational number lies between x and y. Now you may ask the question, but if I assume x is greater than 0, what if x is less than 0? So if my x is less than 0, less than equal to 0, this would imply my minus x is definitely greater than equal to 0. This would imply by Archimedean principle, there exists n belongs to natural number such that minus x is definitely less than n. This would imply x plus n is greater than 0. So this x plus n is positive number. Moreover, x is less than y would imply x plus n is less than y plus n. So I have a two real number, x plus n, y plus n, and out of that one real number is positive. We have just proved this case itself. If we have a two real number here, x and y, such that x is greater than 0, then we can always find out a rational number in it. So now I have a two real number, x plus n, y plus n, which are a two real number. Out of that one real number is positive. So just the case which I have proved, we have proved just now. By that case, we can say that there exists r. Instead of r, I will say some another number. So suppose call it as t belongs to a rational number such that my x plus n is less than t less than y plus n. Now what I will do, I will subtract minus n from each side. What I will get is x less than t minus n less than less than y. But you know that t belongs to rational, n belongs to natural. So n is already part of a integer. So n is also belongs to rational, and rational numbers are closed under addition. So t minus n belongs to rational, and we call this as suppose r. So this would imply x less than r less than y. So hence proved. So irrespective whether x is positive or negative, we have proved that between any two rational number, there is a between any two between any two real number, there is a rational number. So existence of a rational number is very important. After this, one can have an immediate corollary that between any two real number, say x comma y, such that x less than y, there are infinitely many rational number. So this theorem is purely based on the theorem which the density theorem which I have put just now. So if I get a two real number, then I can find out infinitely many rational number. Density theorem guarantees the existence of one rational number. Now here I am saying there are infinitely many rational numbers. So the proof goes follows. So it is given. It is given that x is less than y. So and x comma y belongs to real number. So by density theorem, of rational, by a density theorem of rational number, there exists R1 belongs to rational such that this R1 lies between x and y. Right. When I say R1 belongs to rational number, that means when R1 belongs to Q, that would imply R1 also belongs to real number because the rational number is a part of real number. So R1 is a real number again. So now apply density theorem on x and R1. So I got a two real number. One is x and the another one is R1. So what I can say, I can apply a density theorem which I have proved. I can say there exists R2 between x and there exists R2 which where R2 belongs to rational number such that R2 lie between x and R1. So this would imply there exists R2 belongs to rational number such that x less than R2 less than R1. So I have applied the density theorem on x and R1. But we already know that from this inequality, we already know that R1 is a smaller than y. So which is smaller than y. Now again you can apply the density theorem on x and R2. So on similar way you can continue this process. So you may have x time Rn less than Rn minus 1, Rn minus 2, dot 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 less than y. Here somewhere I will have R. So continue this process for infinitely many times. You will get that there are infinitely many rational. So continue like this. So at the end we can say that there are infinitely many rational number between two real number. Hence there are infinitely many rational number between any two real number. This result seems to be very means maybe you may not initially you may feel that it's a simple, but this gives a lot of it is a very useful in a calculus because in a Riemann integration, that integration and all, we will be this rational and irrational. This property will helps a lot if when you go for the second year mathematics. So there is a calculus paper where the integration and all is needed. So this property helps a lot to in a calculus. So maybe in second year you will realize that, or maybe you will learn this property. We will revisit again to this property. Now since I have proved a density theorem of rational number, on the same line there is a density theorem of irrational number. So density theorem of irrational number. So we can easily guess now what the statement is. Statement says that if x comma y belongs to R such that x less than y, then there exists irrational numbers. Then there exists a small q which belongs to irrational. Irrational means it is not a rational, and irrational is denoted by q complement. So this q, and when I write a c above to q, that is called as a complement. So there exists small q belongs to q complement such that x less than q less than y. Right, so let's go for the proof. So since x comma y belongs to R and x less than y, so by density theorem, of rational number, I am applying now rational number. Um, okay, so what I'll do, x belongs to y, I need to do one more thing here which I added. So what I'll do, this would imply x by root 2 comma y by root 2 also belongs to R, right? This would imply, actually I should have written in the next line. Okay, okay, so x by root 2 comma y by root 2 less than I belongs to R. So this would imply x by root 2 is strictly less than y by root 2. The reason is, since x is less than y, so if you divide by root 2, which is positive number, the inequality remains same. So I got a 2 real number such that x by root 2 is less than y by root 2. So I can apply by density theorem of rational numbers. I can say that there exists a rational number between x by root 2 and y by root 2. So let's write down that. There exists R1 belongs to rational number. It's called belongs to rational number such that x by root 2 less than R less than y by root 2. Now what I will do, I will multiply this inequality by root 2. I will get x less than root 2 times R less than y. Now just look at this number. Small r is a rational number and root 2 is irrational number. Now when you multiply this irrational into rational, you will get a result of a irrational number. So since R belongs to Q, root 2 belongs to Q complement, this would imply root 2 into R belongs to Q complement, that is irrational, and this root 2 times R we will call it as Q. So let this would imply x less than Q less than y, where Q is equal to root 2 times R, which belongs to irrational. So it says that, so hence proved. So what we did is as follows: between any two real number, we found a irrational number. A quick corollary after this is that take any two real number, you can find out infinitely many irrational number between these two real number. Corollary, between any two real number, say x comma y, such that x less than y, there are infinitely many irrational number. Well, I will not prove this theorem. This proof is a homework. This goes similar to what I have proved it for the rational, and I'm sure that you will able to complete this. So with this theorem, we have completed the last theorem of your unit 1. So with this, the unit 1 of calculus is completed. So in upcoming weeks, we will have the recording of second unit, that is sequences in real number. So thank you.